Have you ever wondered how we predict the future? I mean, not with a crystal ball, but with actual data? Well, it turns out the past often holds the keys to what's coming next. Today, we're going to dive into the science of time series analysis to see exactly how it's done. Just think about it for a second. The daily closing price of an index, monthly inflation numbers, the weather forecast, we are surrounded by data that unfolds over time. Being able to predict where those things are headed is absolutely crucial, right? And the tool that makes it all possible is the time series model. So let's start with the absolute basics. So what even is a time series? Well, it's pretty simple, really. It's just a set of data points recorded in time order. Could be daily, monthly, heck, even every single minute. But here's the most important part, the thing you have to remember. The order is everything. This isn't just a random bag of numbers. In a time series, the sequence itself is where all the juicy patterns are hiding. Okay, but there's the catch. Most data you find out in the real world isn't all neat and tidy. No, it's kind of chaotic. It's got trends and seasons that make it a real headache to analyze. So before we can even think about predicting anything, we first have to find some kind of stability in all that chaos. And that right there is the fundamental challenge. We can only build models that actually work when the data underneath behaves consistently. In the lingo, we can only model data efficiently if that data comes from what's called a stationary process. So, what on earth does that mean? Stationarity. This is our holy grail. A stationary series is one that's basically in a state of statistical balance. Its average value doesn't keep changing, and how much it wobbles around that average also stays pretty consistent. It's predictable, because its fundamental character isn't shifting all the time. Look at this comparison. It makes it so clear. A stable stationary series, it's got a constant average. Any random event, a sudden shock to the system, it's temporary. The series eventually comes back. It basically forgets the distant past. Now, an unstable series is the total opposite. It might have a clear upward trend, meaning its average is always on the move. Shocks can knock it onto a whole new path, permanently. And it has a long memory, whereas something that happened years ago can still have a huge influence today. So how do we actually see this long memory? We use a tool called correlogram. It just plots how related a data point is with its own past values. For an unstable series, today's value is super related to yesterday's, which is related to the day before, and so on and so on. The connection just goes on, fading out very slowly. And this long memory makes it almost impossible to predict. Now compare that with a nice, well-behaved stationary series. Its correlogram tells a totally different story. The correlation drops off fast. What happened today is related to yesterday, maybe the day before, but the influence from a long time ago, it's pretty much zero. The series forgets. And that rapid decay is exactly what we're looking for. It gives us a clear local pattern that we can actually build a model around. So how do we get from that wild, unstable mess to a nice, stable series? Well, the main trick is called differencing, and it's a beautifully simple idea. Instead of looking at the absolute price of a stock, we just look at the change in price from one day to the next. By focusing on the change, we strip out that underlying trend, and boom, what's left behind is often a stable, stationary series we can work with. Okay, so we've managed to tame the data. We've got our stationary series, awesome. Now what? Well, now we need to understand its internal structure. What kind of pattern is actually left in there? For that, we've got two key diagnostic tools. Our first tool is the autocorrelation function, or ACF for short. This is basically the same plot we were just looking at to check for that long memory. It measures the total correlation between a point and its past versions, which we call lags. It captures everything, both the direct and the indirect relationships. It's the whole story. The second tool is the partial autocorrelation function, or PACF. Now, this one is much more surgical. It measures the direct correlation between 2 points after we mathematically strip away the influence of all the points that fall in between. It really isolates that pure direct connection. To make this difference totally crystal clear, let's use a family analogy. Think of it like this. The ACF is the sum total influence your great-grandparents have on you. That includes all the traits they passed down through your grandparents and then your parents. The PACF, on the other hand, is just their direct influence, those unique quirks you got from them that didn't come through your parents. It isolates that one-to-one link. So how do these fancy diagnostic tools actually help us? Well, by looking at the specific shapes of the ACF and PACF plots, we can figure out which type of model is the best fit for our data. You can think of these as models with different kinds of memory. First up, we have the autoregressive model, or AR. This model works on the assumption that the current value is just a direct function of its own past values. It's basically like saying today's stock price is, say, 70% of yesterday's price plus a little bit of random noise. This is a model with a direct, explicit memory of its own history. Next is the moving average model, or MA. This one's different. It assumes the current value is a function of past random errors, shocks to the system. It doesn't remember its own past values directly, but it does remember the unpredictable surprises from the recent past. It's a model with a memory for randomness. And now, we can combine all these ideas into the master tool of time series analysis, the ARIMA model. The I in the middle stands for integrated. That's just the differencing we did earlier to make the data stationary. Then, we apply the AR part for the memory of past values, and the MA part to handle the memory of past surprises. It's really the complete package, the all-in-one toolkit for modeling a huge range of data. Which brings us all the way back to our original goal. We've taken a chaotic series, we've made it stable, we've decoded its internal patterns, and we've built a model to describe it. Now, it's finally time to predict the future. Ultimately, this whole process really boils down to 3 steps. First, we just want to describe the data and get a handle on its structure. Second, we build a mathematical model that actually fits that structure. And finally, the moment we've been waiting for, we use that model to forecast where the series is going next. And that's really the whole journey in a nutshell. We force the data to be stable using differencing. We decode the hidden patterns with our trusty ACF and PACF plots, and then we fit a model like ARIMA that captures the data's unique blend of memory and randomness. What we end up with is a powerful mathematical story of the past that we can then project into the future. These tools give us an absolutely incredible ability to learn from history, but it all hangs on one single critical assumption, that the patterns of the past will actually continue into the future. So the final question really is, what happens when something truly unprecedented occurs, and the future just decides to write its own rules? That right there is the ultimate limit of looking backward to see forward.